Today we will solve rational function inequalities. I already did the first problem for us. So for what values of x is x minus 3 over x plus 1 greater than 0? Since we're dealing with a greater than 0 situation, what we can do is we can just use the number line method. We know that the left side of the equation, or the inequality, will equal 0 when x equals 3 and x equals -1. And then it's only going to cross 0 when we change with those boundaries. So I can substitute in something to the left of -1, something between -1 and 3, and something to the right of 3. So essentially what we're doing is we're finding the critical points of the graph. So the critical points are anywhere that we cross an axis or we have an asymptote. And then we end up solving by substituting in some value from this region and figuring it out. So we have two regions of the graph that are greater than 0. And if you look at a quick sketch of the graph, you see that that is true. So -infinity to -1 and 3 to infinity are the correct answers. So let's start doing problems like this. Problem 2, for what values of x is x minus 4 squared over x minus 7 less than 0? So we already know that there are going to be two critical points at 4 and 7. And we know that that's true because anytime we have an x-intercept or a vertical asymptote, then that's going to change, perhaps going to change whether this function is less than or equal to 0. So what we may want to do is we may want to check how this works algebraically. If I sub in something less than 4, for example, 3, I get -1 squared, which is 1, over -4. So 1 over -4 gives me a negative number. If I substitute in 5, I get 1 squared over -2. That's also a negative number. If I plug in something to the right of 7, like 8, I get 4 squared, which is 16 over 1. So that's positive. Now at 4, this function is not less than 0, it is equal to 0. So that means if I'm graphing the function or my solutions, what I would do is I would end up with -infinity to 4 union 4 to 7 as the interval notation of my solution. So now I'm going to scale the x's by 2. So then it's a little bit easier to fit on the graph. I have a vertical asymptote at 7. And what would end up happening is this is going to bounce at 4. And it would look something like this. And we could graph it a little bit better because we know how to do that, but I'm just trying to sketch it for right now because we have a lot of problems to go through. But basically we would have an oblique asymptote. It would look something like this. And my function would be negative from -infinity to 4, 4 to 7, and then it's always positive after 7. Now this one, we have to be a little bit careful because 1 is not 0. So because 1 is not 0, I have to be a little bit more careful here, and I have to subtract 1 from both sides. So I end up with 2x plus 5 over x plus 1 minus 1 is greater than 0. I can deal with this, but I have to get a common denominator in order to really get anything going here. So I'm going to change 1 to be x plus 1 over x plus 1. So then I end up with 2x plus 5 minus x plus 1 over x plus 1. So this ends up being x plus 4 over x plus 1 is greater than 0. And that's pretty straightforward. So I have critical points at -4 and 1. I'm sorry, -4 and -1. And then I'll substitute values in. So if I have -5, let's say, I get -1 over -4. That's positive. If I sub in something between -4 and -1, like -3, I have positive over negative. Then if I sub in something like 0, positive over positive. So where is this greater than 0? It is from -infinity to -4, union -1 to infinity. Now, if I'm using graphing, what I would have to do is I would have to graph this in two different ways. I would graph the function y equals 2x plus 5 over x plus 1. So I know I have a vertical asymptote at -1. I'm scaling this one by ones. And then I have an x-intercept at -5/2. So that would be here. And then what I would do is I would graph this, and I would note that the horizontal asymptote would be at 2. And so I would graph this, and it would look something like this. Yeah, something like that. I didn't do a great job of that. It looks something like this, and then it looks something like this. So I can do a little bit better job, like make sure that this crossed at 5, because I know that my y-intercept's at 5. So I could do a little bit better job of that. But then I would also graph the line y equals 1. And then my objective is to figure out where is this greater than 1. Well, it's greater than 1 everywhere to the left of 4 and everywhere to the right of -1. Now, how do I know that it stops at 4? Well, if I sub in, -4. If I sub in -4, this ends up being -8 plus 5 over -4 plus 1. And that's -3 over -3, which is 1. So I know that these intersect at x equals 4. All right, now I can do this problem similarly. So I would graph, I'll do the graphing method first. So I would do 2x plus 5 over x plus 1. That's the exact same graph as before. So I have the vertical asymptote, horizontal asymptote, and x-intercept, and I know that the point -4, 1 is on my graph. I also know the point 0, 5 is on my graph. And then I have this graph, x plus 1 over x minus 1, and I'm going to graph that in blue. Eventually what I want to see where is the black graph greater than or equal to the blue graph. So that's ultimately what I'm going to try and do, because this one's in black and this one will be in blue. So the blue one is going to have a vertical asymptote at 1 and an x-intercept at -1. And we know that the horizontal asymptote will be at 1. So what I'm going to do here is I'm going to graph this. This would be at -1. And then it looks something like this. So this is not an awesome graph, but what I can do is I'm going to get rid of the asymptotes and just try to, well, maybe I can't get rid of the asymptotes all that well. But what I can at least do is now I can kind of see where the general area of this answer is going to be, just with some sketches. So the black one will be greater than the blue one. It appears from -infinity to somewhere around -3-ish. And then from -1 until somewhere around 2 to 3. I mean, we didn't graph it awesomely, but that would be, that should be our answer, something around that. So I will subtract this over and get a common denominator. So 2x plus 5 over x plus 1 minus x plus 1 over x minus 1 is greater than or equal to 0. So then I will get a common denominator, 2x plus 5 times x minus 1 minus x plus 1 times x plus 1. So basically what I did was I multiplied this one by x minus 1 and this one by x plus 1, because that's what's missing from each of those. And then the denominator will be x plus 1, x minus 1. And this needs to be greater than or equal to 0. I finished the problem off camera to save a little bit of time. So we distribute, subtract, factor, and we end up with x plus 3, x minus 2 over x plus 1, x minus 1 is greater than or equal to 0. And so then we do the number line method, and we see that everything to the left of negative 3, everything between negative 1 and 1, and everything to the right of 2 makes this greater than or equal to 0. So then I have to write my answer, and I see, well, one thing I notice is that I put filled in circles here and open circles here. So that's something that we kind of got to analyze a little bit, because just because we have a greater than or equal to sign doesn't mean everything gets filled in all the time. For example, if you look at negative 1 and 1, those values are not anything that make this work. If I plug in negative 1, the denominator is 0. And likewise, if I plug in 1, the denominator is 0. That means that it's not greater than or equal to 0 at that point. This fraction is not greater than or equal to 0. That fraction is undefined at that point. So I need to have open circles. And so this would be my answer. And then I've done some graphing to show you the yellow is all the parts that work up until negative 3. So negative infinity to negative 3. And then this blue represents everything to the asymptote for the black function. And then the black function takes over between negative 1 and 1. And then the blue function takes over at its asymptote 1. And then starting at x equals 2, the black function takes over again. So that mirrors what happened on this number line method, and it mirrors what happens in the interval notation. So let's do 2 more quick problems. If I subtract this over, I have 1 over x plus 2 minus 3 over x plus 1 is greater than or equal to 0. Then I will get a common denominator. So x plus 1 minus 3 times x plus 2 over x plus 2 times x plus 1 is greater than or equal to 0. So then if I distribute, I will end up with negative 2x minus 5 over x plus 2, x plus 1. And that would happen if I distributed x minus 3x gives me negative 2x, 1 minus 6 gives me negative 5. That has to be greater than or equal to 0. I then factored out a negative from the top to make it easier for me to see that negative 5 halves is one of the critical points. So I have negative 2, negative 5 halves, and negative 1. So I'll plug in something to the left of negative 2, like, for example, negative 10. It doesn't really matter. But that's clearly going to make the top one negative times a negative, which would make the top one positive. And then the bottom would be negative times negative, which would also be positive. So this would be a positive number. Some number between negative 2 and negative 5 halves. If I look at that, that would end up being a negative number. And basically all of these are going to flip one sign. So they're all going to alternate. So I'm looking for things that are positive. So my graph is going to look something like this. And notice I have open circles at negative 2 and negative 1, because that's going to make the denominator 0. So those x values don't actually make the function defined, or the rational expression defined there. So my answer would be negative infinity to negative 2 with a parentheses, union negative 5 halves with a bracket to negative 1 with a parenthesis. Finally, 3x minus 5 over x plus 2 less than or equal to 2. So I'm going to subtract the 2 over to the left side. Then I'm going to get a common denominator, 3x minus 5 minus 2 times x plus 2 over x plus 2 is less than 0. When I distribute the negative 2, I get 3x minus 2x, which is x, and then negative 5 minus 4, which is negative 9. These should be less than or equals. So then I have negative 2 and 9 as my critical points. So if I substitute in something that is I need to write that a little bit better. If I substitute in something that's to the left of -2, I would have a negative divided by a negative, which is a positive. If I sub in something between -2 and 9, like 0, I would get a negative number. And then substitute in something to the right of 9, I would get a positive number. So this ends up being -2 is not going to be part of my answer, but 9 will be, because 9 would make it equal to 0, but -2 would make the fraction undefined. So -2 to 9 would be my solution.